This video covers electric force. Now you know from chemistry and past science classes that charge is a property of subatomic particles. Two types, we have positive, which are protons, and negative, which are electrons. Like charges repel and opposite charges attract. So here in this picture, we have two opposite charged particles, one positive, one negative, and the forces in between them are acting towards each other. They are attracting. At the bottom, we have these two positive charges and two negative charges. So the forces on each of them is a repelling force. It goes away from our two charges. Now, net charge is an isolated system, is conserved, and we're going to see examples of that later. The electrified state is due to a transfer of charge, in this case electrons, from one object to another. If something is positively charged, that means it has more protons than electrons. If something is negatively charged, it has more electrons than protons. So for an object to become positively charged, it has to lose excess electrons. In order for something to be negatively charged, it has to gain electrons. It has to gain electrons. Now, charge is quantized. What that means is Q, which is going to represent charge, is an integer multiple, which is capital N in this case, of the elementary charge E. E is a value of 1.6 times 10 to the negative 19. So a proton has this charge, but it's positive. An electron has this charge, but it's negative. Now, these values, including their masses, are things that are going to be found on the constant sheet, so it's not something you have to memorize. But remember that Q, the charge, is an integer multiple of the elementary charge. Now, when we talk about neutrons, it doesn't necessarily mean that they have no protons or they have no electrons. It means that they have the same number of protons as it does electrons. So these charges cancel each other out. So you can't really tell how many protons and electrons it has. All you can tell is that they have the same amount of both. Now, this equation is called Coulomb's law. Coulomb's law describes an electric force. This electric force is a conservative force. What that means is that the work done by this conservative force is independent of the path taken. Remember that friction is a non-conservative force because the work done increases as the distance increases. But this is a conservative force, meaning that the work done is not dependent on path taken. This equation is also inversely proportional to the square of the separation R. What that means is as R increases, my force should decrease. Now, it's important that you remember here we do have absolute values for Q1 and Q2. The direction of the force is going to come from a conceptual understanding of charges. And R is going to be the distance between these two charges. Now, K in the previous equation is known as Coulomb's constant. It takes a value of 9 times 10 to the 9th. It has units of newtons, meters squared, per coulomb squared. Again, this value can be found on your constant sheet. It's important to be able to locate these on your constant sheet so that you don't have to waste time trying to figure out where you can find this information. That value of K is derived from 1 over 4 pi times epsilon naught, which is a new Greek letter we have not seen before. Epsilon naught is equal to 8.8542 times 10 to the negative 12. This is known as a permittivity of free space. Now, permittivity just means the ability of a substance to store electrical energy in an electric field. And in this case, we're looking at the ability of a vacuum, meaning no air, to store electrical charge in an electric field. Now, consider 2-point charges, Q1 and Q2, that are placed a distance r apart. Problems are usually going to ask you to determine the magnitude and direction of the electric force acting on only one of these charges, in this case, acting on Q2. So because we have a positive charge and a negative charge, we know that the force in between them is going to be an attracting force, meaning the force is going towards each other. This notation is going to be represented by F by 1 on 2. So it's not F12, it's F1 by 1 on 2. If we were to look at the force acting on Q1, which would be in this direction, it would have the exact same magnitude, but it would be labeled as the force created by 2 acting on my object 1, or charge 1. Now, it's more likely that you're going to see these types of problems on the multiple choice section, and they're going to come in terms of these types of problems. In a sense, there is a force F between two like charged spheres. The charge on one sphere is doubled, while the charge on the other sphere is quadrupled. The spheres are moved apart until the distance between them is double the initial distance. The new force between them is, and it has some answer choices. So here, we want to look at the basic equation, which is F is equal to K, Q1, Q2, over R squared. So this is our fundamental equation. What's happening is that we are doubling one of the charges, and we are quadrupling another charge. It doesn't matter which one in this case, because they're being multiplied. And then the distance between them is double the initial distance. So here, R is now 2R, and remember that that is being squared. So if we simplify this, the top part becomes 8, K, Q1, Q2, over 4R squared. Remember that 2 needs to also be squared. This fraction reduces down to just 2. So what that means is we are 2 times the original force, D. In the second example, we have the distance between two charges is halved. The force between the charges is, so again, we want to start with our base equation, which is K, Q1, Q2, over R squared. And now what's changing is our distance is being halved. So this simplifies to K, Q1, Q2 over R squared over 4. Because you have a fraction down at the bottom, you need to multiply by the reciprocal. What that means is that your equation now looks like 4 times K, Q1, Q2 over R squared. Because this is our initial force, we have increased by a factor of 4. Now remember that electric forces are vectors. Forces are vectors, meaning that they need both magnitude and a direction. We can also apply a superposition principle, which means that we are going to sum up all of our forces to find our net force. But just like we did in forces, we need to find all of our forces in the x and all of our forces in the y. Now, before we do a more complicated example, you might see a problem that says, determine the resultant electric force on Q3. Now, in this situation, we have 3 different charges. What you want to do is look at each of them independently. You want to see how Q1 affects Q3, and then go back and look at how Q2 affects Q3. Yes, there are forces between Q1 and Q2, but all it's asking about are the forces on Q3. So, between Q1 and Q2, they are a repelling force. So the force by 1 on 3 is to the right. Now we want to look at the second charge. This is a negative charge, and this is a positive charge. So the force in between them is an attracting one. So this force is by 2 on 3. And this force is to the left. So if we wanted to sum up or find the net force acting on Q3, we would just say the sum of the forces is equal to F13, which is positive because it goes to the right, minus F23, and it's negative because it goes to the left. And if it accelerates or it's allowed to accelerate, it would be equal to mass times acceleration, just as all sum of the forces is equal to. In this situation, we consider 3-point charges. Q1 is equal to 6 times 10 to the negative 9 coulombs. coulombs is the unit for our charge, and it's located at the origin. Q3, which is 5 times 10 to the negative 9 coulombs, and Q2 is equal to negative 2 times 10 to the negative 9, located at the corners of a right triangle. So it's important that we draw a little coordinate system here. So we have one charge at the origin. This is Q1. And we have another charge located, Q2 is located at y is equal to 3 meters. That means we're going to go up 3. And here we'll find our second charge. And this is a negative charge. So we're going to include a little negative here. While Q3 is located 4 meters to the right of Q2. And this is a positive charge. So we want to find the resultant force on Q3. So again, it doesn't matter that Q1 and Q2 exert forces on each other. All we care about is how they affect Q3. Now, if we look at Q2 and Q3, which is this one and this one, this is a negative, this is a positive, so it's a attracting force. So the force is in this direction. This is F2, 3. And the magnitude of this force is equal to K, Q2, Q3, all divided by the distance in between them, which in this case is 4 meters. Now you can actually put in the values of Q2 and Q3 and get a value of 5.625 times 10 to the negative 9. Again, we're putting in all positive values here. And this is a force, so the units are newtons. Now we want to look at Q1 and Q3. Because both of these are positive charges, then our force is a repelling force, and it will act along the straight line in between these two forces. Okay? So this dotted line that I drew here is a straight line in between Q1 and Q3. So the force by 1 on 3 is acting in this direction. So to find the magnitude of that force, we're going to do K, Q1, Q3, all over R squared. Now R in this case, if this is a right triangle of sides 3 and 4, this must be 5. So 5 is the distance between Q1 and Q3. So we can actually get a value for that, which you get 1.08 times 10 to the negative 8 newtons. Now, this force is acting at an angle, off like this. If I want to find the resultant force, I need to add up all the x components and all the y components. Now, because this acts at an angle, we need to solve for the y component and the x component. Now, it doesn't matter how you draw the triangle. You could have drawn it the way I drew it here in blue, or you could have drawn it this way in black. The reason I'm going to use the blue version is because it matches up what my picture already shows. So this inside angle here would be the same as this inside angle here. So to find that angle, we're going to use inverse tangent of opposite over adjacent, 4 over 3. So you get an angle of 53.13 degrees. So in order to find the component of the force in the x and y direction, we need to use F sine theta. This is sine because it is opposite. And we need to use cosine over here. Now this will be force 1, 3 in the x. This will be force 1, 3 in the y. Over here, our force 1, 3 in the x is F, which is this value here, times the sine of 53.13, which gives you a value of 8.63 or 8.64 times 10 to the negative 9. And then you can do the same thing in the y direction. To get a value of 6.48 times 10 to the negative 9. This is a 3. Now, this is a force in the x direction. This is our force in the y direction. Because our force F23 is also in the x direction, then we can write the sum of the forces in the x direction is F13x minus F23, which gives you a value of 3.01 times 10 to the negative 9 newtons. Now, this is the sum of the forces in the x direction. We don't have to do anything to the y direction because there's only one component of the force acting in the y direction. But if this is our force in the y and this is our force in the x, then to find the resultant, we need to Pythagorean theorem these two values. Again, to show you what's happening, our net force in the x direction is now (3.01 times 10 to the negative 9). Our net force in the y direction is a positive 6.48 times 10 to the negative 9. And what we're trying to do is solve for the hypotenuse, the resultant of these two values. So, we simply do the Pythagorean theorem of these two values. (3.01 times 10 to the negative 9 squared plus 6.48 times 10 to the negative 9 also squared, which gives you a value of 7.147 times 10 to the negative 9. So that's the value of this green resultant that we see here. Now, we need both magnitude, which is this piece, and direction, which is going to come from this angle here. So, to solve for the angle, we can do inverse tangent of our opposite over adjacent, which is 6.48 times 10 to the negative 9 over 3.01 times 10 to the negative 9. Which gives you an angle of 65 degrees. So this would be your complete answer. This last example is two weights of mass m is equal to 0.25 kilograms are attached to separate strings of length L is equal to 0.4 meters and hung from a common point on the ceiling. So your situation looks like this. When a charge Q is placed on each mass, the masses repulse and swing out away from one another, forming an angle of 22 degrees between them. What is the charge Q? Well, for this problem, we know that it is in equilibrium, meaning all of our forces are balanced. But because we have mass, we have other forces besides electric forces in this situation. So our free body diagram for one object shows tension, the force of gravity, and our electric force. Now, it doesn't matter which one that you draw it for, but you only need to do it for one. Now, to write the sum of the forces, we can say that this piece will be T sine theta. In this case, theta is not 22, but 11. And this side can be T cosine theta. Again, everything is in equilibrium. So, the forces in the x direction equal Fe, which is our electric force, minus T sine theta is equal to 0. That means they must equal each other. And the sum of the forces in the y direction are T cosine theta minus mg, also equal to 0, meaning that they also equal each other. So if we're trying to solve for Q, Q is going to be found here. We know that our electric force will be equal to K Q1 times Q2 over R squared. So we want to solve for our electric force, or the magnitude of the electric force, so we can eventually solve for the charge. To do that, we need to know what T is. Well, I can solve for T over here by dividing by cosine of theta. So T is equal to mg cosine theta. Now I'm going to plug in this entire equation for T over here. So T is mg over cosine, and sine is already there. You should notice that this becomes mg tangent theta. So my equation becomes K Q1 Q2 over R squared is equal to mg tangent theta. Now you might think, well, I have Q1 and Q2, how am I going to solve for just Q? But it did tell you that the same charge is placed on both of them. So instead of having Q1 and Q2, I can actually replace this with Q squared. Just Q times Q becomes Q squared. Again, I want to solve for Q squared, so I'm going to move R squared to the other side, and then I'm going to divide by K. And finally, take the square root. So that our equation now looks like Q is equal to the square root of mg tangent theta R squared over K. The problem is that we don't know what R squared is. But R is the distance between these two charges. Well, if this is L and this is theta, then this must be L sine of theta. Now remember that R is the distance between these 2 points. So the total distance between Q1 and Q2 is 2 L sine of theta. So we can make that substitution here. Mg tangent theta 2L sine theta squared, don't forget that squared piece, I know I'm starting to overlap here, divided by our value for K, which is 9 times 10 to the 9th. Once you plug in all of your values, you should get a charge of 1.11 times 10 to the negative 6th power. And this is a charge, so we're in units of coulombs.